Bertrand, you're ready?
Yes, I'm ready.
Okay, so welcome everyone for the second lecture of Bertrand Eynard, who will tell us about the two-matrix model. Please go ahead.
Okay, so on peut repasser sur l'écran, sur le tableau. So in fact, so I will start with a blackboard. So last time I showed you that it is possible to compute every angular, so group integral of that type. And the result is amazingly simple. It looks like a sum over permutation signature. And basically, it looks more or less like a determinant, except that in the product, we have matrices. So it's, I don't know, call it matrix determinant, whatever. And all these matrices commute together. They form a commutative algebra. Let me explore a little bit more consequences of this theorem. First, in fact, the matrix M, X, Y, Xi, eta, if you expand it at large Xi and eta, it's identity plus 1 over Xi square, eta square times the matrix A. That depends on the spectral parameters, plus O of 1 over Xi of cube. Okay. On this matrix A of so the pi tilde coefficient is sum of I equals 1 to n of xi y pi over I if pi equals pi tilde. It's 1 if pi tilde minus 1 is transposition, and it's a 0 otherwise. And it also commutes, so this matrix A also commutes with the matrix M's, of course, because it's the limit. So look at these matrices. All these matrices, they all commute together. They all belong to the same algebra of commuting matrices. For instance, A is just sum over I of xi AA. Okay? And so they all commute also with I, with this I, with this matrix I. So, so for instance, you have that this I commutes with A. And this is a very useful theorem. I will show you some consequences of that in a minute. Let me now state the next theorem. So far, this I is the... Okay, let me continue here. So far, the I here was only the integral, the parts of the integral only over the group. We still have to integrate over eigenvalues. And let me show the theorem now. The theorem is that, so what I called H, which was a matrix, pi tilde, but let me write directly the matrix. It depends on my spectral parameters. And remember, I recall you that this was something like expectation of traces of something like xi minus m1, 1 over y pi of I minus m2, 1 over x pi tilde inverse pi of I minus m1, and so on. So expectation values, so this H collects all possible mixed traces expectation values, and it forms a matrix of size n factorial by n factorial. And I'm going to give you the explicit formula for this H. This H is worth 1 over the partition function for normalizing, sum over, let me call rho is sigma n permutation, sorry, sigma n minus 1 rho. There will be an n factorial to the square. Product from k equals 1 to n of mu k sigma of k. And what is this mu? By definition, and it depends, this mu will be an n factorial times n factorial matrix. This mu is an n factorial times n factorial matrix defined as follows. It's a double integral, and not an n by n integral. It's a double. Sorry, it's not a 2n integral. It's an n double integral of d psi d eta e to the minus n v1 of psi e to the minus n v2 of y e to the n c psi eta psi to the k minus 1 eta to the l minus 1 and the matrix M psi eta. So that's the definition of mu. So basically, it's the moment of this. So this is a two-variable measure. And these are the moments of these two-variable measures multiplied by this M. And I recall that this matrix M is just made of simple rational functions that have poles at the xi's and the yi's. And it's a very simple expression. So, so this is the matrix of moments. And this is the final answer. Well, first, you see that all these integrals, since they are integrals of M, they also do commute with all m's, and they also commute. So they also commute with the A, and they also commute with the AI's. So the result here, the final result H, which is a matrix indexed by permutations, also commute with these matrices, and I will show you some consequence in a minute. But let me first talk about the proof of this theorem. Proof. Well, it's a proof like orthogonal polynomials method, exactly like Godin meta proof. First, recall that h of xy was equal to, so if you multiply by the partition function, it was this integral over so the matrix measure was, so we had dm1, dm2, and which you recall was d x, so Vandermonde of x to the square, Vandermonde of y to the square, product over I of dxi e to the minus n v1 of xi, product over I of dyi e to the minus n v2 of yi, and time the group time vi, time what you have here. So we have a sum over sigma minus 1 to the sigma. We have a ratio by the Vandermonde, so we have only one Vandermonde. We have exponential minus sum over I of so minus x minus so plus nc in my notation. Recall that I choose c equals minus 1 over n. Xi y sigma I, and we have this m of xy xi y sigma I. Right? And we have, okay, now, okay. Now observe that the Vandermonde determinant can itself be written as a determinant. Well, once the name, the Vandermonde determinant. So delta of x is product of xi minus xj, but it is also the determinant of xi to the j minus 1. And so it can be written as sum over some permutation rho minus 1 rho product over I of xi to the rho I minus 1. Right, so let's put that in the equation here. So ZH equals sum over sigma minus 1. So we'll have sum over rho, and since we have another van der Waals, we'll have another permutation tau, minus 1 to the sigma, minus 1 to the rho, minus 1 to the tau. We'll have some integral, product over I, dxi, e to the minus n v1 of xi, e to the minus n v2 of yi, e to the nc xi y sigma I, m of x y xi y sigma I. Sorry, it was a big x on the big y, not to be confused. And xi to the rho I minus 1 and yi to the tau I minus 1. Right. So first of all, let us, in the product over I here, let's replace by sigma I. Okay. So here it would be sigma I and tau sigma I of I minus 1. Let's recall tau to, let's recall tau sigma to tau. So basically we recall that tau. This removes this. Now let's, we see that we have a product of independent 2x2 integrals. And we recognize that this quantity is exactly what I called mu rho I tau I. It's exactly mu tau I rho I. Rho I tau I, sorry. So we see that it no more depends on sigma. So we have n factorial times sum of rho, sum of tau, minus 1 rho, minus 1 tau, product over I of mu rho I tau I. Again, changing, since the product is symmetric, we can recall I, we can recall rho I. So you have tau. And again, changing tau to tau rho, we can replace it this way. And this removes that. There is no more rho dependence, so you get an n factorial to the square. And you get that. And you see that this is the determinant. Well, this is exactly what I wrote in the theorem. So we have proved the theorem. So what is interesting with this theorem? First, it gives the exact value of every mixed correlation, mixed traces correlation function. It gives an exact formula that involves moments. But another nice property of that formula is that so this matrix H has to commute with the matrix A. And let me show you, for instance, the example in n equals 2, what this implies. If you write what these matrices mean for for n equals 2, this implies some nice properties, which are the, let me write it this way. The expectation value of trace of 1 over x1 minus m1, y1 minus m2, 1 over x2 minus m1, 1 over y2 minus m2 is equal to 1 over x1 minus x2, y1 minus y2 times expectation value of 1 minus 1 over Cn trace of 1 over x1 minus m1, 1 over y1 minus m2, 1 minus 1 over Cn trace of 1 over x2 minus m1, 1 over y2 minus m2. Okay, minus, and in fact the same thing where you change y1 with y2, so x1 minus m1, and 1 over y2 minus m2, and 1 minus 1 over Cn, trace of 1 over x2 minus m1, 1 over y1 minus m2. All right. So this kind of equality, is an equality between a moment where you have a product of 4 objects. It can be written in terms of traces where you have only 2 objects. So it's typically also the kind of relationship you have in free probabilities. And here it just comes from the symmetry coming from the group integral. So it's just a symmetry of the UN integral. Okay. Now let me move to the next part of my talk. Okay, so
Bertrand?
This was the example for n equals 2. You can write such relationships for higher n's. And typically, you get some link patterns exactly like on the T-shirt that Roland Speicher was wearing this morning. You have such, I mean, you can relate these equations to the kind of...
Bertrand?
Yeah?
Yeah, maybe that's related to what you say, but do you have a combinatorial interpretation of this relation?
No, I don't have a combinatorial interpretation of this relation. Maybe you do, but I don't.
I don't, otherwise I wouldn't ask.
Okay. No, I do not know. So in fact, I'm coming to maps now. So now I'm going to talk about maps. So both sides are generating functions that count certain types of maps. And okay, when you have an equality of generating series, it means there are bijections between the objects that are counted. So there are bijection between certain types of maps and other types of maps. And this bijection is not known by combinatorists. I mean, and we have tried hard to find an interpretation, but we have not succeeded so far. So now let me talk about Ising model. So that will be my second part. Ising model on maps. So first, I need to talk about formal integral. So what is the relationship to matrix models? So remember that I was writing a matrix integral which was on Hn cross Hn, dm1, dm2, exponential, and let me write minus n trace, and I had a over 2 m1 square plus b over 2 m2 square minus c m1 m2, and exponential minus, n trace of sum over k equals 3 to d tk over k m1 to the k plus sum over k equals 3 to d tilde t tilde k over k m2 to the k. Okay? So this is what I was considering so far, and we made some computations. But possibly you want to multiply that by some polynomial of m1 and m2. Right? Well, there is a general theory of how to relate that to combinatorial problems. And the idea is that you need to separate the quadratic part in the exponential and the non-quadratic part. So the very general framework is the following. So let me define something that I will call a formal integral, dm1, dm2. Okay, so in fact, let me rewrite the same expression, formal. And it is defined as follows. So it is not equal to the same we had before. It is equal by definition. So this is really the definition. It's sum from k equals 0 to infinity, 1 over k factorial. Okay, let me call all this term in the parentheses, sorry, even all this. It's a polynomial, you see, it's a polynomial of m1 and m2, but it starts with degree 3. So let me call all this thing the pole larger than 3 of m1 and m2. It's all this n trace, blah, blah, blah. So integral over, now you take hn cross hn. And all these parts, let me call it 1/2 of q of m1, m2, so the quadratic part. So exponential, so dm1, dm2, exponential minus 1/2 q of m1, m2, and this polynomial 3 to the power k, and times this other polynomial of m1, m2. So basically, this is the same definition as before, except that we have exchanged the order of integration on sum over k that reproduces the exponential. 1 over k factorial times this to the k is this exponential, and we have permuted the order of sum on integral. And it's not, I mean, it's not something trivial, and in fact, this is really different from the initial, so from the actual hn cross hn matrix integral. The two are really of different nature. And this one is called the formal one. And every time you have an integral like that with a Gaussian part, exponential quadratic, times polynomial, so this is a polynomial moment of a Gaussian integral, and by the Wick theorem, well, let me call it Wick-Isserly theorem. Then every polynomial moment of Gaussian integral can be written is equal to a sum of graphs, of weighted graphs. So it's equal to a sum of our graphs onto which graph you associate a weight, and this gives a value, and the value is equal to that integral. And weighted graphs, and typically the weights, you have Q inverse, the quadratic form inverse per edge, and so you have graphs made of vertices, edges. The weight per edge is related to the inverse of matrix Q, and the weight per vertex is related to the coefficient of this polynomial. I do not want to enter the details, but when you work this for the two matrix model, when you do this for the two matrix model, what you find is exactly some maps that can have two colors. So now let me move to my slides. Just a minute. Okay. So I will. I don't know if I can show a pointer. Okay. So my. Sorry. Oh yes, it's here. Sorry. So can you see the mouse? Can you hear me?
Yes, yes,
Okay.
we can see
Okay.
the mouse and we can hear you.
Okay. So let me move to the next. Sorry. Where is the slideshow mode on Windows? I'm not sure. Okay, excuse me, I'm not familiar with this computer. Okay, I will do it by hand. So what are the Ising model maps? So the Ising model maps are maps where you have triangles, let's say triangles, but also quadrangles on other faces. And these faces can carry two possible colors, either plus, I hope you can see, or minus. And these are the rules to construct the map. So you have a certain number of triangles that carry a plus. You have a certain number of quadrangles that carry a plus, a certain number of pentagons that carry a plus, and so on. You have also triangles that can carry a minus, quadrangles that can carry a minus, and so on. And you have also some faces that are marked faces. So here it's an example of a face. And by marked face, I mean there is marked faces have one edge that carry an arrow. Okay, and you have a certain number of marked faces, and the marked faces are labeled. You have a marked face number 1, the marked face number 2, and so on. And these marked faces have a length L1, L2, and so on. And typically, you are going to compute. So look at this WGN. WGN is the sum of all maps of genus G. That can be drawn in genus G. So this one in this example is drawn on the plane. It's genus 0, but you can draw some on the torus or and so on. And the weight that you associate to it is T3, the coefficient T3 of my polynomial V1, multiplied by the number of triangles that carry a plus, T4 by the number of quadrangles that carry a plus, and so on, and T tilde 3 per triangle that carry a minus, T tilde 4 by quadrangle that carry a minus, and so on. And for the labeled marked faces, you put 1 over x1 to the length of the first marked face plus 1, 1 over x2 length of the second marked face plus 1, and so on. And what makes it really interesting, the relationship to the Ising model, is that you have also a weight per edge, and you put a weight C++ per edge that are between plus and plus faces. So an edge that separates 2 plus has a weight C++, an edge that separates 2 minus has a weight C minus minus, and an edge that separates a plus and a minus has a weight C plus minus. So this is our model of maps, and typically we want to count, to take the sums over such maps. And what I claim is that this sum is exactly equal to the formal matrix integral that I was describing before. Okay. But here, the marked faces, so see here the marked face has only plus on its boundary. So it will be related to non-mixed traces. We shall also be interested in faces with non-uniform boundaries, and that will correspond to mixed traces. Well, first, before going further, let me rephrase, let me put this model in a little bit different way. So the same WGN, so the same partition function, can be obtained from another model of maps, which is the following. So you have the same, more or less the same ingredient. You have triangles, quadrangles, and so on that will carry the same weights, T3 to the power number of plus triangles, T4, and so on. 1 over xi per length of marked faces, and so on. But now in this model, I have an extra piece, a diagon, which has one side of color plus and one side of color minus. So this is an extra piece to compare to the previous model. And now also in these maps, I do not allow to glue faces together if they, along an edge if they have different colors. So I allow only same color on both sides of an edge, but I allow this piece that somehow allows changes of colors. So this diagon allows the changes of colors. And now I take a sum over all such maps with nearly the same weight, but now I put a weight 1 over A per plus plus edge, 1 over B per minus minus edge, on the weight C per diagon. For each diagon, I put a weight C. And I claim that if these weights A, B, C are related to my weights C plus plus, C plus minus, C minus minus by this relation, so this matrix is the inverse of that one. So I claim that if they are related by this relation, then the generating functions that I'm computing here are exactly identical. They are the same. Okay. The explanation is very simple. In order to glue together a plus and a minus, you need to insert diagons. You can insert 1 diagon or 3 diagons or 5 diagons and so on. It's a geometric series, and when you sum the weights of gluing such a diagon or 3 diagons or 5 diagons on all of them, when you sum them together, you get the geometric series gives C over AB minus C squared, which is precisely the C plus minus that corresponds to the inverse of the matrix. So it's just to say that you have 2 different ways of phrasing your Ising maps, either with the diagons or either without the diagons, that computes the same generating functions. Okay, so let me come back to my generating functions. So as I was saying, WGN is the generating function that counts maps where all marked faces carry only plus. And you have n of them, first marked face of length L1, second marked face of length L2, and so on, and you take this sum. And you sum over L1, L2, and so on. Okay, so it's a function of x1, x2, xn. Okay. I recall that v prime 1 was this quantity, ax minus sum of tk xk minus 1, and for convenience, it's useful to rewrite that a is minus t2. Okay, same thing for the b's. And it's also convenient to define the following functions. So W01 is what I will call the disk amplitude. It will play a really special role. W01 means 0 means planar, and 1 means only one marked face. So typically here you have an example of map that contributes to W01. It can be drawn on the plane, and there is exactly one marked face with only plus, and one marked edge along the marked face. That's here. And okay, what we want basically is to compute W01 on every WGN on many other generating functions that count maps. But let's start by computing W01. In fact, it's convenient to make a shift W01 by V prime 1, divided by C, and call this new function y of x. It contains exactly the same information as W01, but the equations will look nicer in this function y of x rather than the function W01. And if you want to recover W01, you just make the shift again. Okay, you could also compute, so here it's a tilde. You could compute the tildes, W tilde GNs. It's exactly the same thing, except that I consider marked faces with only minus. So the W tildes have only minus on their marked faces, and in particular you can have a W tilde 01, the disk amplitude with one boundary with minus signs, and you shift it now by V prime 2 and call this function x of y. Okay, so just some definitions. Now I also write some other generating functions. This UK is, I hope you can read. Isn't it too small? Okay. UK is, again, a sum over maps. Can I enlarge that? Okay. UK is, again, a sum over maps with more or less the same weight. Okay. But here, the mark, so UK will mean genus 0. And there is only one marked face, but this marked face has a certain number of plus and a certain number of minus. And in fact, UK means the K here is the number of minus. And for the number of plus, it's L1, and you sum over L1 with the weight 1 over X1 with 1 over x to the power L1 plus 1. So it's a function of x, and for each k, you have such a function of x. Let me also define, so let me sum over k. So you sum over k with a new spectral parameter y in this way. So it's a sum over k with the uk's, and you form a function of two variables, which you call W01. It's basically the sum of these uk's, and again, you make a certain shift, which will be convenient for writing the equations. A shift by v prime 2 and by c square x. Okay. You could do that also for higher genus maps with higher number of marked faces, but let me ignore that for a moment. Let me also consider the function h on, well, let's focus also again on the genus 0 and the 1 marked face. Basically, now you have, again, a marked face. So this h means you have a marked face, but you have now an arbitrary number of plus and an arbitrary number of minus, and you sum the plus with 1 over x to the L plus 1, the length of the plus part, and 1 over y to the L plus 1, the length of the minus part. So it's this term here. Okay. Another one is the PGN, which is a polynomial in x1 and y. Again, focus on the genus 0 and n equals 1 case, so you don't have this. You don't have these other faces in the denominator. And again, it's a sum over maps with a certain number of plus and number of minus, but the number of minus and the number of plus is maximum equal to d minus 2 or d tilde minus 2. So it's a polynomial in x and y, this PGN. It will be important. Okay. This h is the one I was doing on the blackboard a minute ago. It's the one I've computed a minute ago. It's the one that has an arbitrary number of faces, and all faces are mixed faces. So each face can have a certain number of plus, a certain number of minus, a certain number of plus, a certain number of minus, and so on. And you collect all of them to form a matrix indexed by some pi and pi tilde that correspond to how you go from one component of the edge to the next. Okay. So these generating functions defined with maps are more or less the same I was considering with the two matrix model. Now, let me try to compute them. And we shall write tut relations. No, sorry. How can I go to full screen? Okay, does anyone know where is the slideshow button here? Well, okay. Okay. Tut equations are equations, so typically it's what Elba was doing for the one matrix model. So without plus or minus on the faces, but typically it's the same kind of thing. So we have this generating function uk of x, which is the generating function that computes maps, where that are planar, and with only one marked face. So in fact, in this picture, I put the marked face on the exterior, and the rest of the faces in the interior. So the marked face is the one that is exterior, and it has a certain number of plus on its boundary, and it has exactly k minus on the boundary. And the marked edge is the first plus that follows a minus along the boundary. So I want to compute the number of such maps, and I will do by recursion on the number of edges. So Tut's equations are recursion on the number of edges. So what happens when we remove the marked edge? So you erase the marked edge. There can be several possibilities. On the other side of the marked edge, you can have some gone, some plus gone, a j gone, and then it has weight tj. And that corresponds to that term in the generating function. Another possibility when you erase the marked edge is that on the other side of the marked edge, there is the digone. And when you erase the digone, you increase the number of minus by 1. So basically, you get the uk plus 1 with the weight c, because this is the weight of the digone. And another possibility is that on the other side of the marked edge, you have the marked face itself, like that. And when you erase it, you get two disconnected maps. One that has, again, k minus on its boundary, and one that has only plus on its boundary. And in terms of generating function, this gives this product, UK times W01 times the discamplitude. Okay? And the initial terms mean that in this recursion on the number of edges, you have to be careful about what happens for very small number of, for when the length of the face is small, you have to be careful. So basically to the initial conditions in the recursion, and that corresponds to adding some polynomial of x that I'm not going to write. You see that these relations, can you use them to really compute this function, these functions UKs? Well, not really, because you see that each time you increase k by 1, and so you have an infinite number of equations, but none of them, I mean, they don't close, because each time you increase k by 1. So to close them, you need another equation, and the other equation is now, consider U1, so the generating function of maps that have exactly one minus sign on the boundary. And now erase the edge with a minus sign. What happens? On the other side, you can have a j-gone with a minus. So you get this weight t tilde j and some uj minus 1. Or you can have a digone. And if you have a digone, you see that now you have only plus signs. So you get c times the discamplitude, and again minus initial terms. If you put everything together, you can find a closed equation for the U01. So basically you sum over here, you sum over k. And you find a closed equation for U01, which is this equation. I just ask you to believe me, but it's the equation you find. Now, this equation is really nice. It allows to solve the problem. Why? So this is the equation you get. But this equation is valid for every x and every y. In particular, you can choose the small y to be related to x by the function y of x. So basically, you choose small y equals big Y of x. This cancels the left-hand side. Well, this is also known in combinatorics as the Kernel Method by Bousquet-Melou and co-authors. So just choose y to be y of x. The left-hand side cancels. And then it implies that the right-hand side where you place small y by y of x must be 0. So what you get is this equation. And look at it. It is a polynomial equation in both x and y of x. So it's an algebraic equation. It means that y of x is solution of a polynomial equation. It means that y of x is an algebraic function of x. And basically, it determines completely this y of x. So basically, this equation determines the discamplitude. It determines W01, and we see that W01 is an algebraic function of x. And it obeys this equation, this polynomial equation, E of xy. So the right-hand side here, let me call it E of xy. It's this polynomial. You see it has degree d in x and degree d tilde in y. This is the Newton's polygon of this polynomial. So basically, I put a dot whenever you have, so at position ij, if there is a coefficient for the xi, yj in this polynomial. And it always has such shape. And so basically, this determines the discamplitude, this determines W01. So let me summarize a little bit what we have. So we have found that y of x satisfies this equation. And so we know W01 of x like that. And also now we can, so now since we know the discamplitude, the third equation can be used to also find the U01, now with arbitrary y, and it's just this ratio. So again, it's a quite kind of simple expression. Now we could have done also the same thing with the W tilde. So now let's redo the same computation, third equations, with the minus sign instead of the plus signs. And you will find that the function x of y, which is the W tilde 01 shifted by v prime 2, satisfy an equation. And in fact, it is the same e. It's important. The same e, the same polynomial of two variables, can be used to determine the discamplitude as a function of x, the plus discamplitude, and the minus discamplitude as a function of y. It is the same equation, which means that functionally the two functions x and y are functionally inverse of one another in terms of multi-valued algebraic functions. They are inverse of one another. This is a remarkable result. This is deeply related to the notion of symplectic invariance that Elba was mentioning this morning. This is also very deeply related to the Matic-Sin equations in random matrices. This is a very deep result. And also, let me say that by writing again Tutt's equations, you can find the following result. The function h01 of xy, which was computing mixed traces, so one face, so planar, one face, but the face has two colors on this boundary of arbitrary length, and it's equal to that. So now I will leave the slides and go back to the blackboard. Okay, and I will start again from there. So the relationship between maps and matrix model, and formal matrix model, is that, so for instance, in the formal matrix model, if we, so I defined Wn of x1, xn was the cumulant expectation value of trace of 1 over x1 minus m1, trace of x1, xn minus m1, so only m1s. It is, so as I said, it is the sum of our maps, and the weight is 2 minus 2g, so 2 minus 2g minus n, sum from g equals 0 to infinity of wgn of x1, xn, where this quantity is maps, is what I just wrote. It's the generating function for maps that have genus G and n marked faces with a plus. Okay. Similarly for all the others, and for instance, on what I will call, and you see that W01, the planar one, G equals 0, is somehow the leading term in the large N expansion. It's also called the planar. So in the formal matrix model, you can call it the planar limit. This is also what people are interested in free probabilities. You want to extract the large N limit. Here it's formal large N limit, but you can extract it. Okay, and okay. So I will say that W0, so W0n of x1, xn. Let me call it the planar okay. Okay, and otherwise it would be, I mean, the GIF term in the 1 over n expansion would be the genus G term. Okay. Right. So let me summarize what we obtained so far. So we have an equation E of x, y of x equals 0, which determines W01 of x, which is v prime 1 of x minus c y of x. We have the equation E x of y equals 0 that determines W tilde 01 of y equals v prime 2 of y minus c x of y. We have this U01 of x, y, which was, I recall, the expectation value planar of trace of 1 over x minus m1 v prime 2 of y minus v prime 2 of m2 over y minus m2 plus cx squared minus v prime 2 of y. And I said that this is equal to E of xy divided by c, I think minus c, y minus y of x. and this function h01 of xy, which was the expectation value planar of trace of 1 over x minus m1, 1 over y minus m2. And let me put 1 minus 1 over nc. And it is equal to E of xy over x minus x of y, y minus y of x. And I think there is a minus c here. Okay. So, and again, this one counts maps with one plus boundary, so plus plus everywhere, planar maps. This one counts the same kind of thing with minus, 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 minus planar maps. This, and the interesting one is this one that counts a face where you have a certain number of plus and a certain number of minus planar map. So now we know this generating function, we know this generating function, we know this generating function. And first remark, once you know the disk amplitude, so once you know the disk amplitude, you know this polynomial E and vice versa. If you know the polynomial E, you know the disk amplitude of plus signs. And you see that knowing the disk amplitude with plus signs implies that you know the disk amplitude with minus signs. And it also implies that you know the disk amplitude with a mixed boundary condition, mixed traces. So mixed traces are determined by non-mixed traces. And they are furthermore determined by only plus non-mixed traces, for instance. So now we want to go further. And I will give you a result. No, it's no longer written on the blackboard. But let me now compute. So a little bit further before, at the beginning of this lecture today, I showed you that the group symmetries implied, so the fact that you commute with this A matrix implied some relationship between the expectation values. And if you take the planar part, in fact, what you get from what I said before is that the trace of 1 over x1 minus m1, 1 over y1 minus m2, 1 over x2 minus m1, 1 over y2 minus m2. This expectation value planar. And I think you take a minus 1 over nc in front. So which is counting, so it is counting some things like you have one marked face, again planar. So on a planar map, you have one marked face, but now you have two changes of boundary conditions. Okay, so we have a certain number of plus and a certain number of minus. The x1 is, and you have a marked edge, so basically all this part is correct. So if you have L1 such things, it will be weighted by x1 to the L1 plus 1. So all this red part will be associated to the variable x1. So let me redraw this picture in this way. So this is, so let me put the marked face as a circle. And this is the map. And on this circle, you have the variable x1, the variable y1, x2, and y2. Okay? Whereas this one, the h01 was counting objects where you have just an x1, an x, on the y. On this one, we have computed, it is equal to this quantity. So now group integrals tell us that this quantity is equal to 1 over x1 minus x2, 1 over y1 minus y2, times h01 of x1, y1, h01 of x2, y2, minus h01 of x1, y2, h01 of x2, y1. And that's it. Okay, so basically this formula, which came from the symmetries of the UN integral, tell us that the generating function of such maps is related to the generating function of these maps by a very universal formula. You see, this formula it does not depend on the potentials, for instance. It does not depend on the t case or on the t tilde case. It's a very universal formula. Also, you see that this generating function is a product of h01s with typically it's a product of h01 of xi, y sigma I, and some other permutations with a coefficient c sigma of x and y. Product from I equals 1 to n. And in fact, this will be general. In fact, again, by group symmetry, or, okay, this equation which I'm writing here can be deduced from the group symmetry. It can also be proved by Tutt recursions, exactly the same kind of Tutt recursions by removing edges and so on. But basically, it can be written just as a consequence that it commutes with a matrix A. So let me state the next theorem, and I think I will stop here then for today. So if we define, so the expectation value of, so planar again, of trace of 1 over x1 minus m1, 1 over y1 minus m2, 1 over x2 minus m1, and so on, 1 over yn minus m2. Okay, so which is associated to this kind of boundary. So you have x1, x2, x3, and so on up to xn, and y1, y2, and up to yn, okay, is equal to sum of our permutations. You have this coefficient c sigma of the x's and the y's, a universal coefficient, and product from I equals 1 to n of h01 of xi, y sigma I. So basically, it tells you that once you know the function h01, you know all such amplitudes. And what are the coefficients c sigmas? And moreover, c sigma is non-zero only if sigma is a link pattern. What I mean by that is that you see sigma associates, it associates an x with a y. It's a permutation that sends the x's to the y's. So let me draw it as arrows, arrows on that picture. For instance, x1 can go to y2, x3 can go to some other place, and so on. Okay, and I want, so for instance, xn could go to y1, but this is not a link pattern. There is a crossing. So basically, I want non-crossing. So it means non-crossing So you should sum over only sigmas that are non-crossing, and this is basically the T-shirt of Roland Speicher. So you have, you can have such pictures. I don't know, I mean, okay. Just invent some of them. And what is the value of C sigma then? What is the value of C sigma? And I think it's time to stop. So for instance, just as an example, in the case of n equals 2, so if we, so in the case n equals 2, we had two permutations, the identity and the transposition. Both are non-crossing. And the coefficient was 1 over x1 minus x2 times 1 over y1 minus y2 for the identity, and minus that for the transposition. And in general, there is a formula for C sigma, but I think that I will give it next time. So there is a closed formula for C sigma, which is just a rational function made of all the xi's, and that can be entirely read off from the link pattern. And basically, it's a product of 1 over xi minus xj and yi minus xj's along the faces of that graph. And I will give it next time. So first, thank you for your attention. And I just want to comment what I'm going to do next time. So next time, so here you see I'm computing only this kind of mixed traces. So we have only one trace, fully mixed, but genus 0, but I'm considering only the genus 0 part and only one trace. The goal next time is to have an arbitrary number of, a product of an arbitrary number of traces, all of them fully mixed onto every order in 1 over n, so every genus. And for that, we shall need some recursions that look very much like the topological recursion. But the idea is that once you know the disk amplitude, so once you know W01, once you know non-mixed traces, basically, you know everything. You can know everything by some recursion, similar to topological recursion. Thank you for your attention. In fact, I cannot hear you.
Now, can you hear me now? Sorry.
Yeah, yes, yes, sorry.
Thank you for your lecture. Are there any questions? What about the Zoom audience? Any questions from the Zoom audience?
Hello, I have one question. So you said for arbitrary number of boundaries, mixed boundaries and genus, you have this Tut-like equations, but do you have the same theorem that you, I don't know, can give an explicit expression, not only in recursive?
No, it's not as explicit. However, what we have is that the symmetry, so the commutation with the A matrix holds to all orders. And for any number of traces, and this commutation relation with the M and A matrices is an extremely powerful tool. And basically, it says that many expectation values are related together, and eventually it says that any expectation value can be related to only expectation value of the type trace of a bilinear, I mean, trace of only two things.
Is an explicit expression known for two boundaries, for two mixed boundaries?
Yes.
Okay.
I've got a question for Bertrand. It's Jamie Mingo here from Canada. So in the upper right-hand corner of the board you're standing in front of right now, you shaded in one of the little regions between the lines marking the non-crossing partition.
Sorry, I'm not sure I...
Yeah, that upper right-hand corner?
Yeah.
That picture you drew, yeah, you shaded in.
Yes.
So
here, you mean?
Right, yeah, so is that just, I mean, there's a convolution formula for when you have freely independent random variables where you do one non-crossing partition on one of them, and then the Crevasse complement on the other one.
Yeah.
And that's how the Crevasse complement, it's the region in between the lines. So is that what you're doing in that picture?
I think so. I mean, okay,
Yeah.
we should discuss together. And I did not give a formula yet, so I'm just saying that we have this formula. So this mixed trace in the planar. So what I call planar is exactly what you call free probabilities.
Yeah.
Okay, I think it's exactly the same thing.
Right.
So so I'm just saying, so the theorem that I mentioned here is that it is a sum over all non-crossing partitions with a certain coefficient, which is a rational function, times this product. And now this coefficient, I was just saying that it's zero, it's non-zero only if it's non-crossing. And I said that I will give a value next time. And I think that's what your question is about. I was not, I mean, it's a little bit long, so I cannot do it in 5 minutes. But I want to give a value, and the reason why I shaded these faces is that the value of this C sigma is a product over faces.
Okay, yeah, that looks
and
like
next time I will say exactly which product, and it satisfies the recursion, and hopefully it's the same as what you have in pre-probabilities, but I didn't check.
Yeah, I didn't get to see Roland's talk this morning because I just got up. And but in the case of this higher order freeness, and I think I can see Piotr sitting there in the third row, that he could comment on this too. But the idea is that you take cumulants of traces of resolvents, and when you do that, the highest order term is always planar.
Yeah.
And so, and then you can go backwards. I mean, once you go the cumulants, then you can go back and get the moment. So the idea is you switch to cumulants, and then at each level, the thing that you're interested in is always planar. And so you never go outside the case G equals 0. It's just that you have many more faces. The number of faces will go up, but it's always genus 0. I mean, that's sort of the idea of the theory, is that everything can be reduced to a genus 0 case by taking enough cumulants. So if you don't mind taking lots of cumulants, you can always reduce it to genus 0, which is, I think, kind of interesting. But maybe Roland has talked about that this morning. I haven't had a chance to watch his talk yet. Yeah, but we'll see in your next lecture.
Okay, any further questions or comments? No, that doesn't seem to be the case. Then let's thank Bertrand again